the concept of RL load. So let me start with uncontrolled half wave rectifier with RL load. So uncontrolled meaning the diode will be used, the power diode will be used. So the circuit of half wave rectifier goes as follows. This is a power diode, and then you have a RL load. This is my Vin, which is normally, we can also call it as Vm sine omega t, right? This Vm is the peak voltage. But once I write over here 230 volts, 50 hertz, what does that mean? It's a RMS voltage. Are you getting it? Yeah? And it's a single phase supply. This is my power diode. This D is my power diode. This is my R and this is my L. Let me write R and L inside. R and L. And this is my output voltage. Okay, fine. Now, the explanation of this circuit might be very simple. When the diode turns on, it acts as a short circuit, so V out will be equal to V in, right? And when the diode is off, in a negative half cycle, the output will be equal to 0. Correct? It's a simple lag raha hai, but it's not that simple. It's slightly complex with the RL load. So listen carefully, very, very carefully over here. So let me try to draw the input waveform first. Okay. Now I am drawing my input waveforms over here. Only one cycle is enough for time being. So this is my input. Fine. Now, whenever you have a RL load, my output voltage is actually, if I apply a KVL over here, what is my KVL in this circuit? When the diode is on, let's say when the diode D, power diode D is on. When the diode is on, it behaves as a short circuit, right? So when the diode is on, it will behave as a short circuit, correct? So what will be my KVL over here? My V in is actually will be equal to V out. Correct? This much agreed? Yeah. Now what is my V out? My V out is a combination of two voltages. One is VR and another is VL. Agree? They are in series, right? So voltages will add it. So I can write in the next step over here, V in is equal to, what is V out? VR plus VL. Now let's say the current flowing through the circuit is I, current I. Now I can rewrite it as V in is equal to, what is VR? I into R. So I into R. Now what is the voltage across the inductor when the current is flowing? You must have studied. L di by dt. Correct? So this is L di by dt. Okay? And one more thing I want to share with you all. When will inductor be act as a short circuit? Whenever the current flowing through the inductor is constant. When will the inductor behave as a short circuit? Whenever current flowing through the inductor is constant. Why? Because derivative of a constant is 0. So whenever current is constant, inductor will behave as a short circuit. This you remember. Okay. Now, so far this thing is clear. This equation is clear to you. Okay, fine. Now, as soon as I apply a positive supply, as soon as I apply an input voltage in the positive half cycle, this is my positive half cycle, right? My current starts flowing. Why? Because diode on ho gaya na. I am using a power diode, so I am neglecting the turn on voltage of the diode, which may be around 1 or 2 volt, and this is around 230 volts. So I am saying as soon as my input goes to positive half cycle, this diode is on. Okay? So only thing I have in the picture is the current starts rising slowly, right? So let me draw the current over here in blue color. So my current starts rising. Okay? From zero only. Because my diode is forward bias, I'm neglecting the forward drop and my current starts flowing. So that means according to this equation, let me rewrite this equation over here. V in is equal to IR plus L di by dt. So my current is changing. That means di by dt will be positive. Current is not a constant, current is increasing. That means this will be positive, right? Well, IR will be positive, R is constant, I is increasing. This also is positive. Okay? This is positive and V in is also in the positive half cycle. So far so good. Now see what I am doing over here. I can rewrite this expression as V in minus IR is equal to L di by dt. Agree? Correct now? Now, in case of a resistive load, when there was a resistive load, let me quickly explain that. When there was a resistive load like this, I have a diode and I have a resistor. Right? This time, what will be my this equation? It will be V in minus IR is equal to 0. Correct? L hoga hi nahi na? There is no L component. So whenever a diode is on, my equation will be V in minus IR is equal to 0. Right? In this case, can I write V in and IR is equal same? What I am trying to imply is, when I plot the waveforms over here of V in and IR, will they be coinciding? Yes. Why? Because in a resistor, current and voltage are in same phase. So if this is my V in, this will be my, let me draw it properly. I hope it is visible. So how will my I in will be? I will be. What I'm saying, magnitude might be different. Huh? What will be the magnitude of this? V in upon R, Vm upon R. Magnitude it will be differing. What I'm saying is, they will be in phase. In case of resistive load, this is my current in phase with the voltage. समझ में आ रहा है what I'm saying? So this was the picture in case of R load. This was the picture in case of R load, resistive load. Okay, now in our case we have L also. Now let's see what L is doing. Okay, now what I was saying, the current is increasing, so I is increasing slowly. Now I is increasing, it will reach a maximum value. Now when it will reach a maximum value, as I am increasing the value of I, what will happen? My V in minus IR will approach 0. So तुम बोलोगे कैसे? Listen over here. When V in minus IR, how it will approach to 0? See, R is constant, I is increasing. So some point of time, the magnitude of IR is nothing but VR, voltage across the resistor. At some point of time, my V in voltage will be equal to IR drop. So that particular time, my maximum my current will be maximum. Let me draw that current over here. Let's say it's increasing and it has reached the maximum point. At this point, my V in minus IR is approaching 0. Means what? What is the meaning of this statement? V in minus IR is becoming 0. Let's say that whenever this happens, now whenever V in minus IR has reached 0, my current will be maximum. My current will be maximum. I'll explain you why. The moment, inductor stores energy in the form of magnetic field. So whenever my di by dt is positive, inductor is storing the energy. See, whenever we applied a V to this circuit, it has two jobs: to dissipate the energy across the resistor and to store the energy across the inductor. So जो energy across the resistor है, ये देखो, VR. This energy which is dissipating across the resistor is lost. It cannot recover back. बराबर ना? Energy across the resistor cannot recover back. That is lost. But the energy across the inductor is stored in the inductor in the form of magnetic field. and that energy can be used again, retrieved back. Are you understanding? V in has two jobs. The number one job is to dissipate the energy across the resistor as long as the diode is on, and store the energy across the inductor. So whenever di by dt is positive, my inductor is storing energy. So L stores energy. Okay? Fine. Now let me draw another picture of, let me draw in orange color, IR. So IR also will follow the same wave shape as I. This is I. This is I. Dotted line waveform is I. Current flowing through the in the circuit. So let me draw IR. IR also will follow the same nature. Why? Resistor hai na? IR. Follow the same nature, right? So this component over here is IR. And what about this one, earlier one? This was I. Oh. This dotted line was I. Right? Now you tell me, if this is V in, this black color one is V in, this red color one is VR, what is VL? What is the energy stored in the inductor then? Correct. So see now here, this is, see, I'll repeat, this is VR, right? This is VL. This L di by dt is VL. So I am asking, V in is this black color, right? This blue color is my I, red color is my I into R. That is VR actually. ये VR है. So where is my VL? This is VL. इनका difference. V in minus IR का difference is VL. Let me highlight it over here with a yellow color. So the highlighted portion over here is my VL, right? Let me write over here, this is VL, which is positive. Okay, if you integrate this area, this yellow color portion is my energy stored in the inductor. My yellow color portion which you see over here is my energy stored in the inductor. So energy is getting stored and my current is reaching maximum. Uske baad kya hota hai? Now what happens? Please see here. Now this much is clear to you. What is black color? V in. Red color? VR. So V in minus VR will be VL. That is L di by dt. So actually my yellow color shaded area is my energy stored by the inductor. Because my di by dt was positive. It was storing because current is building up now. Whenever current builds up in an inductor, it stores energy in the form of magnetic field. That's the property of an inductor. Okay, this much clear. Now pay attention please. Now what happens? See, very very interesting. Now what happens? V in minus IR has become 0. Correct? Earlier V in was responsible for VR and VL. Matlab V in is equal to VR plus VL. Now what happens over here? V in cannot contribute more to my inductance. Because now what is happening? Now if my current reaches max value, now it will start decreasing. Now when the current starts decreasing, what will happen next? That means V in minus IR will become less than 0. बराबर है? मतलब V in is not sufficient to provide dissipation across the resistor. मतलब V in को दो जॉब करने हैं. एक तो dissipation across the resistor and storing energy across the inductor. तो stored energy तो हो नहीं रही है अभी because that is equal to 0 and now it's becoming less than 0. So what will happen next? So what will happen is current will reduce. Why current will reduce? I will explain now. Now इसके बाद क्या हो रहा है? My current is reducing now. Now why current is reducing? That also I will explain. My current is reducing. Now why current is reducing? Because as soon as V in minus IR becomes 0, the energy, the stored energy in the inductor will now try to return back the energy. Now listen carefully. What is RL? L acting as a load, right? RL is acting as a load. Load matlab energy later. It's taking the energy from the source. V in source, it's taking the energy. Now, when the current across the inductor is reducing, slightly reducing, right? and V in minus IR has become 0. Current has reached the maximum value. What will happen? The energy stored inside the inductor, now it will give it back. So when the inductor energy is given back, the stored energy is in the form of magnetic field, it will get defluxed. You know energy flux equation in an inductance? Phi in an inductance, you know that formula? I'll write it down. Wait, let it be. Just give me a minute. I'll write that formula over here. A little background about inductor is also required. Let's say that you have this conductor and you have a coil wound around this conductor. Okay, and you have the application of a voltage. This current flows through that coil, and let's say the voltage across this coil is V coil. Okay, a current carrying conductor is acting as an inductor. Right, now over here, this is my symbolic form representation of an inductor. The current flowing over here is I, let's say, and the voltage applied across the coil is V coil. Let's consider that. Now what is this voltage given by? We know the voltage across the inductor will be given by L. But when I say inductor is storing energy in the form of magnetic field, it's generating magnetic flux. Now what is that flux given by? Phi B, which is, don't write this is not necessary. Mu, it will be into N square, number of turns into area, divided by L, length of the conductor. Okay, and this will be multiplied by current flowing through the inductor. Okay, I, let's consider IL. Fine. Now this constant we know it for L. This is L actually. Okay, we say phi B is proportional to IL. That means phi B proportionality constant क्या हो गया? L, and this L is this, which we call it inductance. It is actually reality में this. What I'm trying to say is, when the energy across the inductor, it was storing the energy initially. Now when the current has reached the maximum value, now it will give away the energy back, return the energy. When it is trying to return the energy, it is defluxing. Okay, when it is defluxing, your phi B is reducing. Agar phi B is reducing, L is a constant, right? Phi B is reducing, what will happen to current flowing through the inductor? It will reduce. The current will reduce. That's the reason why over here the current is reducing, not increasing more. Are you understanding? Yeah. So up till here, up till max value, it is clear. Now why the current is falling down, it is clear. Because the inductor is now trying to give back the energy which it has stored when the current was rising. Now it is giving back the energy. Now why there is a need for giving back the energy, that also I'll explain. Because V in cannot supply for VR. Because V in cannot supply for VR also now. Right? Because why it is happening? V in minus VR is becoming less than 0. But on the right hand side we have L di by dt. Right? So yeah, have you understood why does the energy decreases? Because inductor is de-energizing, giving back the energy. That's why flux will reduce. That's why current across the inductor will reduce. This is clear? So this will fall down, and eventually after some time it will go to 0. Okay? It will go to 0. Now let me highlight some point over here. Let me use a brown color. Okay? Now in the negative, in this phase, now whatever phase I'm marking over here, green color, shaded area, that is the region where the inductor is releasing the stored energy. So this is that area. Inductor is releasing the stored energy. This is that area. Green color portion represents what? What it represents? VL is negative. VL is negative now, because energy is stored over here in negative direction. Energy negative means what? It's not taking energy, it's supplying energy. In this case, in this scenario, whenever inductor is giving back the energy, your inductor will no longer act as a load. It will act as a source itself. It will not act as a load, it will act as a source which is providing the energy. So in this case, let me add over here. Now what will happen? B in minus IR will be equal to L into minus di by dt. What I've said earlier above, whenever di by dt is positive, L is storing energy, right? Correct? Now di by dt is negative. Why di by dt is negative? Because current is reducing now. See over here, current is reducing. The blue color waveform is my current. Current is reducing. So if the current is reducing, if I reduces, my di by dt will be negative. And whenever my di by dt is negative, my inductor will release the stored energy. Okay? So inductor releases the stored energy. Is this point clear, everyone? Now how it will act as a stored energy releaser? So how that will happen? See here. Now I can add, now what I can do is V in, this become plus, I can take it this side. Now what will happen? Inductor, when it is releasing the energy, it will join hands with the V in supply. Matlab V in and L di by dt will have the same supply. So matlab, I will show it over here. Initially the supply, the polarity across the inductor is like this. But after it is, releasing the energy, the polarity across the inductor changes this way. Now this will keep the diode forward bias, even though the voltage is going negative direction. See, V in is going negative, na? So that should turn off immediately. But in this case, the voltage across the inductor will also supporting V in keeping the diode in the forward direction, in the forward bias direction. So the current will continue to flow even though the V in is going negative. This is the very, very important confusion which students have. उनको लगता है the current will be zero once the V in is negative. No. In case of RL load, the current will continue to flow. The current will continue to flow little more even though the V in is negative. And who is acting as who is helping him out? Inductor is helping him out. So all this energy, the inductor which is has stored, actually this yellow portion and green area should be same. Because inductor can release the stored energy, that much energy as it has stored, right? So actually in reality this yellow color portion and this green color portion area will be same mathematically. Is this understood? Yes or no? Yeah. Now at what point, listen carefully now, this is understood to you? So very, very important question which we ask. Why does the current still flow inside a RL load whenever we have a RL load, whenever V in is negative half cycle? Whenever there is a RL load, why does the current flows even though V in is negative? This is the answer to that question. Is this clear? I don't know how much you have understood, but in reality, this is what happens. And why I say uncontrolled? Because we don't have any control when does the diode turn on. The diode turns on when does the diode turn on over here? The diode turns on over here, right? And when does it turn off? It turns off over here. Is it under our control? No, it is happening naturally. So to mathematically find this value, this is called as beta. And this beta is called as extinction angle. Extinction angle. And this will be applicable to SCR also. That's why I'm not directly explaining SCR, I'm explaining with the diode first. Is this understood? First of all, your current waveform and voltage waveform are not in phase. ये याद में रखो. Current will be leading the voltage. Always remember, if you have not understood, so far whatever explanation is provided, just remember this, your current will be leading the voltage in case of your whenever you have a RL load. That's it. So in this case, why do we call it uncontrolled? Because on is also not controlled, off is also not controlled. So mathematically, we can find this value at what exact point will this current stop and go to zero. And when the current goes to zero, of course, the inductor has released all its energy. And again, it has in the next cycle, it will start to store energy whenever di by dt is positive again. Remember, di by dt positive, inductor stores energy. Di by dt negative, inductor will release the stored energy. Is this much clear to you? Any questions you all have? Yeah? Clear it is? Yes? Now, let me quickly show you. I told you now this beta, what is the exact, equation of that? At what point we can find out? Now, listen very, very carefully. Everyone, pay attention, please. This is, now I'm not going to write, I'm just going to show you all some things. This is, pay attention on the board. This is a half wave rectifier with RL load, uncontrolled wala, right? Now, where could we use RL load? Why RL load is very, very important? It could be used to drive a DC motor. Now, when we say a DC motor, a DC motor will have an internal resistance and a winding. That winding will be your L. Okay, a DC motor, right? So a DC motor will be required to provide a power to the field winding and the armature winding of a DC machine. So RL load is associated with DC motor, right? It's called uncontrolled rectifier because diode cannot make its own decision to turn on and off. Okay, so far so clear? This is my V in, Vm minus Vm, period of the input signal. Clear about this up till now? Now, this is my ideal IV characteristics of a diode. Diode will conduct, the positive current flows through the diode. It does not have any voltage across it when it conducts. So this red color is the portion where the diode is on. When you apply negative voltage to it, that blocks the negative voltage. And the current across it is zero when it is off. Matlab, if you apply a positive anode voltage to respect to a cathode across a diode, it will turn on. And when it will turn on, it will not dissipate any voltage across it. It will not have any voltage across it, right? The voltage across it is considered as zero by power diode. Okay? So remember this fact. Okay. So over here, during the positive half cycle, the diode is on. During the positive half cycle, the diode is on, and during the negative half cycle, the diode is off. As simple as it gets, right? So when the diode is on, this is what the situation is. That is what we have just now talked about, right? When the diode is on, it behaves as a short circuit. So my input voltage will be equal to V out. So by KVL, V in is equal to VR plus VL, right? Because V out is VR plus VL. What is V in? Vm sin omega t. And what is VR? IR. VR is IR and VL is L di by dt. If I want to find the exact value of current flowing through the circuit, I have to solve this equation. It's a first order differential equation, right? I have to integrate it. So the solution, I am not discussing the solution of it. The solution of this differential equation will be this. So this is my I of t. So I of t will contain two parts. One is steady state sinusoidal response, which will remain, and which will have a natural response, transient response, which will die out eventually, right? So it will contain two parts, steady state solution and transient solution. So this is my steady state solution, Vm upon square root of R square plus omega L square. This you don't have. Fortunately, this you don't have. I'm just showing you the exact expression. Sine of omega t minus theta. I told you now, the current will lag the voltage. Okay? Because of inductance. And here we'll have, this is a constant A, e raised to t upon L upon R. Fine, this is a natural response. So if you wish to find the initial condition, we have to substitute t equal to 0 in this equation. Whenever you substitute t equal to 0, you'll get the value of A. So A will come out to be Vm sin theta divided by square root of this factor. So finally, this is my exact expression of I of t. So this equation number 1 will represent I of t, current. Okay, fine. And these are my waveforms. I've explained you this. See this green color waveform? This is my current flowing through the RL load. See, it's not stopping over here, it's stopping over here. And this angle is called as beta. So during that time, my diode remains on, even though the Vin is negative. And when the diode remains on, what will be the voltage across the diode will be 0, na? And it will remain 0 up till here. Up till here. And when the diode turns off, the voltage, the entire Vin voltage appear across the diode. So here it is. It will follow the input voltage. What about the load voltage? When the diode is on, my load voltage or my V out is equal to V. So whatever is my V in, it will follow that dotted line, the orange color waveform. So the diode turns off at beta, at omega t equal to beta. So when it turns on, turns off, the voltage across the output will be 0. Okay, because when the diode turns off, it will behave as an open circuit. No current flows, the V out will be 0. So here it is 0 over here. And then again the cycle will repeat. Are you understanding? So because of RL load, your V out is going negative. Normally क्या होना चाहिए था? At pi it should stop, right? In case of resistive load, it will stop at pi, but it will continue to conduct till beta. And why it continues to conduct till beta, I have explained that part. Okay, fine. And the higher the value of L, this beta will increase, the delay. That delay in conduction will increase more and more. So the beta will shift towards the right hand side. And remember, beta will be between pi and 2 pi always. Okay. Now mathematically, if you want to find, no, this equation, this shape of I of t, it's not sinusoidal. It's defined by this equation. So this, if you try to plot it in MATLAB, it will give you this wave shape. This wave shape is not a complete sinusoidal like. Okay. Now let me show you the exact expression. So in order to find beta, we have to substitute omega t equal to beta, right? So if you substitute it in this equation, you will get this equation. Because at omega t equal to beta, current is 0. So you have to solve this equation. Now it will not be an easy task to solve this equation. You have to use a computer. So if you solve this equation, that will give you exact value of beta. But remember one thing, the beta will be between pi and 2 pi. Okay. And actually it's not called as conduction angle. It's called conduction angle in case of diode, but in case of SCR is called as extinction angle. Okay. Any doubts so far? Aya? Yeah. Yeah, we are finding beta from this. We are finding beta from this by substituting over here omega t equal to beta and current is 0. So this equation is equal to 0. Now solve it and find the value of beta. No, you don't have this. Mathematically in your syllabus you don't have to find this. Huh? Here it is, here from this equation. Yes. But we take a guess कि beta will happen that way. We just take a guess. And it will be between pi and 2 pi. Yeah, this much is clear to you? Any doubts if you have? In short, long story cut short, if you have not understood so far whatever we have discussed, just remember this. In case of a RL load, whenever we have a V in, your current flowing, the current flowing to the circuit will not stop at pi. It will slightly be beyond pi and will stop at beta. Mathematically, if you want to find that beta exact location, we have to solve that equation which I have shown here. And this beta will be between pi and 2 pi. Is this clear? More towards the pi side. Yeah, whenever di by dt is negative. Yes, and why the current reduces, that also I have explained. Because inductor is trying to de-energize. defluxed. Okay, clear? Now shall we start with our part, what we have to discuss so far? Yeah. So write down over here, controlled half wave rectifier. Now everyone please write half wave rectifier with RL load. Okay? How will the circuit look like? Draw the symbol properly. Okay? While I was checking the paper, some of you all have drawn the symbol like this. No, don't laugh. Your people make mistake. This is wrong. You will simply lose marks. That's it. So please take care of the RL load. This is my V out. Let's say that this thyristor, this SCR is called as T, capital T, T1 let's say. This is my V in, which is Vm sin omega t. Yeah, please. Now we have to just draw the waveforms for this circuit. In drawing the waveforms, we will explain the working also. Now we have to combine two concepts. First is, when does the thyristor turn on? Second, what happens when the current flows through the RL load? So if you have understood both the concepts, draw the waveforms one after the other. Some people are drawing it 1, 2, 3, 4. ऐसे नहीं draw करते. Draw one after the other. Take entire supplement if you want. But draw one after the other. Are you all ready? Let me revise once. How does the SCR conduct? Those who have missed it out. Okay, what are the conditions required for to conduct, right? So when does the SCR turn on? Please listen, those who were absent prior. When does SCR turn on? That is the condition. So what is the number one condition? SCR should be forward bias. Forward bias or forward blocking mode. So SCR should be in, should nahi, must be in forward and next a gate trigger impulse should be applied. And how large should be the impulse? Like this only. Now some people in the exam have drawn the pulse equal to the half cycle ऐसे. इतना मोटा pulse नहीं चाहिए. It will be wrong. You require a short impulse like this. So this you apply at the gate. This is called as IG. Now let me also quickly discuss the all the operating regions. I mean 3 modes of operation of SCR. If this is the current flowing through the SCR, this is the voltage across the SCR, right? What will be this region? What will be this region? Region number 1, forward blocking mode. Here SCR is on or off? Now I am drawing another region over here. I am repeating this because this is important. When SCR is on, region number 2, what is the region called as? Forward conduction region or forward conduction. And then the last one over here, SCR is off. So what's the difference between 1 and 3? Region number 1 will block forward voltages and region number 3 will block negative voltages. SCR is off in both the places. So when we say SCR must be in the forward blocking region, मतलब यहाँ पे होना चाहिए, मतलब SCR के across it should be forward voltage. Okay, and then when you apply a trigger pulse, it will jump from 1 to 2. And when the SCR is on, the voltage drop across the SCR is almost equal to 0. Okay, so whenever SCR is on, it will be like behaving like a short circuit, and the voltage across the SCR will be 0. And whenever SCR is off, the voltage across the SCR, it will behave as an open circuit. This you remember, that's it. Is this clear to you? Yeah? Now let us come back to this. Okay. Please concentrate over here. Of course, we have to show the trigger impulse. Now next time whenever you draw a circuit, show trigger impulse like this. IG, arrow inside, that means you have applied the trigger. Don't leave the SCR like this only. It indicates that you are applying a trigger impulse. Please concentrate now. We have 11 minutes left. Please concentrate for this period. And let me draw the waveforms now one by one. I'll take the reference circuit and I'll explain, I'll simultaneously draw over here also. Okay? Okay, fine. Now everyone please pay complete attention. Yeah. So this is my Vin, no doubt about that. Everyone draw Vin perfectly, right? Then gate impulse. Gate impulse has to be applied between what values? Gate impulse must be applied between 0 and pi, not 2 pi. 0 and pi. Okay? Yeah? And here in this case alpha is less than 90 degree. You can apply anything. But if they tell you to draw the waveforms alpha equal to 45, alpha equal to 90, then you have to follow the trend. Here alpha is equal to 90 when it reaches the maximum value. Half of that will be, I explained last time, right? Over here alpha will be equal to 90. Okay? So for the time being we are not doing it. Now we have applied IG value. I have applied IG. So from 0 to alpha, listen carefully. Omega t is going from 0 to alpha. What is my state of SCR? Is T1 on or off? Off. Off na off. If T1 is off, it will behave as an open circuit. How will my circuit look like? Right? And here we have V out. What will be my V out? Will it be 0 or will it be equal to V in? 0. Why 0? Because current over here is 0, right? Okay, na? Correct? So simultaneously over here, if I draw over here, if I draw current I, this is current I, that current will be 0 over here from here to here, right? Before alpha it will be 0, na? What about my voltage across the output? Zero. Correct? What will be my voltage across the SCR? Remember, V in is equal to VSCR plus V out. So V out is 0, so V in will be equal to VSCR. Matlab, as your V in is behaving, same way your VSCR is behaving. Voltage across the VSCR is same as V in. So this dotted line is my V in. This is voltage across T1. So it will be clear? Yeah. Now let us come back. Now we have applied the gate trigger. Now we have applied gate trigger alpha. So what happens at t equal to alpha? Your T1 is turning on. When T1 is turning on, what happens? Please look on the board. Everyone, when T1 is turning on, the circuit will behave like this, right? It will behave as a short circuit. Now tell me, this is V in, the current starts flowing, right? And what will be the current now? Current waveform. The current will slowly increase, reach max value and decrease. Correct? So how it will happen over here? Current, it will increase, reach the max value and then decrease. Okay, it might not be a sinusoidal wave, and exact sinusoid nahi hoga. And this value is called as beta. Are you following what I'm trying to say? This is beta. This is my current waveform. Fine. Now, in this case, what will happen now to the voltage? V out voltage. V out voltage will be equal to V in, because voltage across the SCR will be 0. अब ये कब तक 0 होगा? As long as the current flows. As long as the current is flowing, the SCR turns on only. अभी देखो, यहाँ पे negative cycle चला गया ना? V in has gone to negative half cycle, but still the current is flowing. So what is keeping SCR on? Energy stored in the inductor is keeping SCR on. V in nahi. This I don't have to explain now again over here, right? So as long as the current is positive, my SCR will conduct. So as long as I flows, your T1 is on. When it will turn off? Current reaches 0. So as soon as I is equal to 0, your T1 is off again. And again the same cycle will repeat. Okay? So somehow we have to mark this below. Let me mark it over here. So when you also draw, please start drawing the waveforms yourself also. So somewhere around here. Please start drawing the waveforms. Are you all following? Can I continue and then you can continue? Now, we have drawn the waveforms up till 0 to alpha, right? 0 to alpha tak banaya na? Now from alpha to pi, the current is positive, and from pi, this is pi, right? From pi to beta, again the current is positive. Now I need not explain this why it is positive. I've already explained that in the initial half an hour. ये तुम्हें याद रखना है. When you draw, you have to draw it like this. Yes? No? You're following? Whenever we have a RL load, this will happen automatically. Turning on of SCR is under our control. We are deciding when it is turning on. But when it is turning off, SCR turns off at T equal to beta, right? We cannot decide that. We don't know that. In order to know that, we have to solve that equation which I have shown earlier. Fine? Now, from alpha to beta, whenever T is, going from alpha value to beta, my current is flowing. That means at this time my SCR is on. SCR is on means what? What is my V in equal to? What is my V in equal to? What is my V out equal to? V in, right? So V out will be equal to V in means what? The answer is everyone please over here. Whenever my SCR is on, my output will be equal to V in. Matlab whatever is the wave shape of V in, it will follow that. Look here how to draw it. From alpha to beta. पहले क्या होता था in resistive load, it is stopping over here. But now it will continue up till here. Because V in is equal to V out. Right? Now what happens after that? What is happening to the thyristor voltage? V of T1. Thyristor voltage is 0, so it will go to 0 up till beta. Okay, what about yeah, current we have already drawn. Current we have already drawn, right? Now what happens after that? From beta to 2 pi, from beta to 2 pi, what happens? The current is 0, T1 is off, thyristor is off, मतलब क्या? ये condition आ गया. When the thyristor is off, what happens? The voltage across the SCR is equal to V in and V out is equal to 0. Correct? Now see here how I am drawing over here. Current also will be 0 only, na? Current is 0 now. What about the voltage across the across the load? Pi tak na? This is pi, this is alpha, this is oh sorry. Yeah, this is beta. This will continue till 0 till pi, right? Okay, 2 pi, yeah. 2 pi. From beta to 2 pi, my thyristor is off. So the voltage across the load will be 0. What will be voltage across the thyristor? Equal to V in, right? So it will follow V in. Follow V in means what? This, right? Up till 2 pi. Yeah? Now, what will happen? We apply again trigger pulse at 2 pi plus alpha, right? So from 2 pi to 2 pi plus alpha, what is my state of SCR? Off है ना? Because trigger pulse नहीं आया है. So what will happen? Whenever t is from 2 pi to 2 pi plus alpha, what is my state of SCR? Off. And when my state of SCR is off, same thing will continue. My voltage across the output will be 0. Voltage across the SCR will be equal to V. What about the current? 0. SCR on ही नहीं हुआ ना? So same wave shape will continue over here, right? So this current will be continuing to 0. Barabar? What will be voltage across the SCR? Across the output? 0. What will be the voltage across the thyristor? SCR? And now I apply a trigger pulse at 2 pi plus alpha. Now again my SCR will turn on. SCR turn on. My output voltage will be equal to, my current will start flowing. तो current किधर तक जाएगा? Till where it will go? Yes, it will go 2 pi plus beta. Somewhere around here. I am not showing, it will repetitive. Okay? And during this time, my voltage across the SCR will be, voltage across the output will follow input. Right? Voltage across the SCR will be 0 till 2 pi plus beta. Right? So this will be the waveforms. These will be the waveforms. While explaining the part by part, you are writing also the working, right? So I explained you the working as well as the waveforms. So kindly note it down. Try to draw it on your own. Try to draw the waveforms on your own. So this is how you explain half wave controlled rectifier with RL load. Everyone understood? Any doubts? This dotted line is my V in, reference V in. And what is alpha? Called as? Not delay angle. Alpha is the delay angle or firing angle or triggering angle. So at omega t equal to alpha, my SCR is turning on. And at omega t equal to beta, My SCR, see, everyone, whenever omega t is equal to alpha, I am controlling it. So turning on is under my control, right? But omega, whenever omega t reaches beta, it is not under my control. It happens naturally. So SCR turns off naturally. So whenever SCR turns off naturally, this is called as line commutation. Whenever SCR turns off naturally, it is called as line commutation or natural commutation. Just remember this. Now please draw the waveforms. Have you all understood how to draw the waveforms? Don't buy hard anything. Only you have to decide when will the SCR turn on, when will the SCR turn off, and what all things will happen. And try to do it yourself first and then cross check it. Will you all complete on your own? You all have understood the concept. Don't try to remember it. So next time we will derive the average output voltage formula, RMS output voltage formula for this half wave control rectifier with RL load and solve some numericals. Okay?